The Ruth Patrick Award is a very special award and very near and dear to my heart because it focuses not only on the aspects of science but also the aspects of management and policy. And the Ruth Patrick Award honors outstanding research by a scientist in the application to basic aquatic science principles to the identification, analysis, and or solution of important environmental problems. It's my sincere pleasure today to be able to introduce the winner of the 2008 Ruth Patrick Award, and that is Professor Rick Batterbee from the University College London. Rick has made outstanding contributions to the reconstruction of environmental change. He's played a very pivotal role in the development of diatom microfossils as a paleolimnological tool, and also has pioneered the application of transfer functions. He initially started to work on acid rain in the 1980s and applied these techniques and tools to acid rain. And then he turned to other important environmental problems such as eutrophication and climate change. These tools are not only widely used by scientists today, but they're also used by managers and by policymakers, which I think are extremely important. Rick has received already many awards, just as a few, and already by 1989 he was recognized for his research on acid rain and was awarded the Royal Geographical Society Back Award. Queen Elizabeth II has made him pioneer of the nation for his helping in environmental advice to solve problems. And in 2006, Rick was elected as a Fellow of the Royal Society of London. He has been very active in the service of science. He has been the leader of a world-renowned group called the Environmental Change Research Center at the University College London. He's also been very active in IGBP and different leadership roles within that organization. And finally, he's also spearheaded a number of large community projects, not only at the UK level, but also at the European level and international level. I think it's quite appropriate as well, because Ruth Patrick was a pioneer in the use of diatoms as biomarkers in streams and its application to water quality. And it's appropriate because Rick also studied diatom fossils and has done unique applications for the management of aquatic systems. And so I think it's very appropriate that he is the recipient of this award. And with that, I would like to invite Carlos Duarte up to present the award to Rick.
So it's an honor for me to present the 2009 Ruth Patrick Award for Environmental Problem Solving to Professor Rick W. Batterbee. And I read the citation: for outstanding contributions to the reconstruction of environmental changes from biological and chemical records in lake sediments, information and techniques that are now in common use in assessing the environmental status of lakes and have become critical tools for lake management and policymakers. Thank you.
Good morning, everybody. Thanks for coming out so early. Could I thank Carlos, John Downing, Dan and his committee, John Small for his citations, and those reviewers, referees out there. It's nice to know we do have some friends. It's a great honor to receive this Ruth Patrick Award. As Dan has said, it's a happy combination for me, Ruth Patrick, because she was an outstanding diatomist, And from ASLO, an organization very close to my heart, the first organization I joined as a young postdoc back in 1973. I naively joined at the time because I was about to submit my first science paper, and I thought that by being a member of ASLO, maybe limnology and oceanography would be actually more sympathetic to my paper. But I'd also like to accept this award on behalf of our research group back in London, the Environmental Change Research Centre, where over the years I've been fortunate to be associated with a large number of postgraduate students and postdocs who have not only done the hard yards, as they say, but also been the intellectual bedrock of our work. And I'm also delighted because together with John Small, who received the Evelyn Hutchinson Award a couple of years ago from ASLO, to some extent this represents the real coming of age of paleolimnology as a discipline recognized by the limnology community. It wasn't always the case. Paleolimnology now, I think, is accepted as a very legitimate tool to be used in tackling major limnological environmental issues. And a good example of that is the work that we're doing, funded by the European Union, in this major project on the global change impacts on freshwater ecosystems in Europe. And problems like what might climate change, how might climate change affect freshwater ecosystems, it demands a combination of a whole range of different skills and expertises, not one of which by themselves are capable of tackling the problems. And so in the Eurolimpacs project, we couple paleolimnology to look at longer timescales, analysis of long-term data series. We use space for time substitution with major data sets spanning the climate space of Europe. Of course, with experiments, both field and lab and mesocosm experiments, and an extensive amount of modelling, both statistical modelling and process-based modelling. All have unique contributions to make. And paleolimnology is one of those techniques that allows us to put our contemporary systems into context over time. Clearly, it has weaknesses, as everybody is well aware. There are problems of preservation often. Quite often, almost certainly, we have problems of dating. Sediments are not always as uniformly distributed in lake basins as you would like. And of course, we're dealing with a historical technique, so our explanations are essentially inferential processes and not directly observed or measured. But we have key strengths. The technique provides a unique perspective on the current status of lakes, provides a method for generating and testing hypotheses about causes of limnological change, provides a methodology for testing models across a range of variability outside that of the observational time series we use. In many cases, it can enable lake ecosystem responses to specific past events to be assessed. And more, it provides a starting point for restoration ecology. It wasn't always the case, as I mentioned earlier. If we go back more or less to the beginning of paleolimnology, to the 1940s and 50s, debates centered very much around long-term lake evolution, pioneered by many people in Europe and in North America, but particularly by Ed Davey. And the discussions were about whether lakes became progressively eutrophic since their origin after the recession of the last ice sheet. Did they become naturally eutrophic quickly or slowly? Did they carry on being eutrophic over the whole of post-glacial time, or did they reach some kind of trophic equilibrium and then stabilize? And then other people pointed out in the 1950s that not all lakes perhaps followed this trajectory. There were those lakes, perhaps in more boreal regions, on more resistant bedrocks, where the evidence suggested that acidification was one of the dominant processes on these timescales. So we had these concepts already in the 1940s, 1950s of eutrophication and acidification from the analysis of lake sediment cores, but these were discussed as natural long-term processes. And of course, one of the questions we have at the present day is the extent to which we can actually separate the impact of people on eutrophication processes and on acidification processes. But the timescales being considered at that time, these were millennial timescales, thousands of years timescales, the postglacial period being about 10 to 11,000 years long. And because of those timescales and the fact that contemporary limnology were not working on long time series in those days, and that paleolimnologists were not working on very recent sediments, there was a real disconnect between paleolimnology and limnology. In fact, this continued right the way through the 1950s and 60s into the debate about cultural eutrophication of lakes. And when I began my PhD in 1968, working on the eutrophication of Lough Neagh, we still didn't really have the full range of techniques that we needed to make a meaningful contribution to that debate. In Lough Neagh, there'd been a major cyanobacterial bloom in 1967, and one of the questions was that because it was a hot summer, or was this lake actually polluted? What is the time context to assess that particular question? We had at that time no historical data whatsoever for the lake, and that was the case for most lakes suffering from eutrophication at the time. We had no previous concepts to work on, few analytical techniques, and the most important deficiency, we really didn't have a dating technique that allowed us to date the recent sediments. So this was my very first diatom diagram from a core I took in 1968 from Lough Neagh. And quite clearly, it was possible to show that there had been major changes. And here, going back to 30 or 40 centimeters down this sediment record, there was a clear switch in the diatom communities from Cyclotelep towards Stephanodiscus, which indicated the beginning of eutrophication. Quite clearly, some time before the 1967 algal bloom had occurred. But the question was, when was that switch? We didn't have Lead-210 dating at that time. It was very difficult to assess dates. Radiocarbon dating was insufficiently accurate to be precise about this transition. And I used at the time a combination of pollen dating and paleomagnetic techniques, and I arrived at a date of this point here of about 1700, 300 years or so before. I was quite wrong. Later on we found it was about the turn of the 20th century, and we were dealing with a eutrophication process that had been ongoing at this site for about 100 years. And we now know that that's fairly typical for many sites suffering from eutrophication. So we were developing techniques in the 1960s during that eutrophication debate, but we didn't really have the techniques developed sufficiently to make a major contribution. But by the time we got into the 1970s, late 70s and the 1980s, we were in a much better position. And I guess fortunately almost for diatomists and paleolimnologists, we had this major concern about the acidification of lakes. And what was the reason for the acidification of lakes? There were many different hypotheses at the time before it was finally shown that it really was a problem of acid deposition. There were many alternatives, and most prominently that land use change might be responsible for acidification, or that we might have been dealing with the end product of a long, slow natural acidification that I referred to earlier. Well, the great thing for us at that time was that Lead-210 dating, which has been the bedrock of recent paleolimnology over the last 20 or 30 years, had been developed in the 1970s. And here you can see a Lead-210 diagram from famous Loch Ness, showing a series of ages going with depth down a sediment core back to about 1850. So that's an excellent technique for dating sediments over the last 100 years or so. And if we couple that with evidence from weapons fall out that are well known and well dated and usually observed in sediment cores in 1963, we can often most usually establish fairly good parameters for recent sediments. And coupled with that, of course, was the need then to be able to be more quantitative in our approach, and this occurred with essentially the development of the transfer function technique. And although there were transfer functions around at the time, it was really John Burke's, Calliter Brack and Steve Juggins in the acid rain program that made these transfer functions much more numerically robust.
And across the paper they published in 1990, Diatoms and pH reconstruction has been the source of much good nautical reconstruction ever since. Essentially, the transfer function is trying to formalize a numerical relationship between diatoms collected from a series of lakes across an environmental gradient compared with contemporary water chemistry, in this case pH, to establish such a relationship at the present day so that we could take samples from sediment cores in the past where the diatoms then could be used to reconstruct the chemistry of the past, or pH in this case. And the strength of these relationships is exemplified here in this early data set from our surface water acidification project, which simply compares the measured pH of 167 lakes across northwest Europe and the pH estimated from the diatoms. So in the acid rain days, we have this useful combination of accurate dating and a numerical technique for reconstructing past chemistry. And so we could use these techniques with many lakes arranged experimentally across different gradients to be able to test these different hypotheses about the causes of acidification. An example is just shown here from a acidified lake in Gower Lake in Scotland, where we can see quite clearly changes in the diatom floor indicating acidification. We can date those changes. In this case, this particular change took place at the end of the 19th century, and we can transfer those biological changes into a chemical reconstruction for pH and show that this lake decreased its pH by about half a pH unit over the next 100 years. And then we can begin to see the way that I couldn't say quite so clearly from May 1967. Many people thought that afforestation in this catchment of the 1970s might have been the cause of the decline in trout populations. But clearly, once we were able to date 1976 and record this level, we will be able to show that the acidification began well before the catchment was planted with conifers. Well, as a result of this kind of work, both in terms of acidification research and eventually in terms of eutrophication research, there's been a lot of interest amongst limnologists and paleontologists about the extent to which the measures that have been taken to reduce acid deposition, the measures taken to reduce nutrient level, have been successful, and how lake systems might respond to legislation. But of course, at the same time, we're beginning to realise that climate change is going to have a major effect as well. So we're left with a somewhat different situation now, that we're not only expecting lakes perhaps to respond to the responses, to respond to changes from single stresses, but they also have to take into account climate change and the fact that osmosis systems are subject to other stresses as well. So we have a conceptual diagram here that summarises that position to the future. Starting back in the past, in the 19th century, most of our lakes were in very good condition. And the changes to the present day, because of stress, the release of that stress, and optimistically going back to something that we had before. But clearly continuing stresses, so that's not likely to occur with conditions in the future are going to be always different from in the past because of that changing stress pattern, changing variability. But also with climate change, we can't assume that the natural baseline, varying how it might be, is constant. We can already see the climate is changing, and we expect it to change somewhat strongly in the future. And so we have a problem that our baseline is shifting as well. And the future state of our lakes is very difficult to predict. And we need this time trajectory, this sense of time over these decadal periods to see the way that systems are changing. And it becomes very important now in the context of, certainly in Europe, legislation that requires managers, governments to restore lakes to their ecological status. A directive, or a further directive, that doesn't yet include a provision for climate change. The question is, to what extent is climate change already affecting our lakes, and can we detect it? Well, we ask this question with respect to lakes which are dominantly affected by eutrophication acidification. These two stresses are usually much stronger than the climate stress, and it's very difficult to disentangle the two. And some paleontologists have been looking at more remote sites to see if we can separate the effect of climate change, where we can perhaps assume that other stresses are not so important. And the major programs, our major programs around the world, in Europe, North America, in the polar regions, looking at remote lakes, mountain lakes here. And here a photograph of John Smalls from the Canadian Arctic. But the timberline will be on written down, including no people living in the catchments. We might expect that these lakes to be absolutely distinct, showing a change through time, and the big sediment falls from them. But if you look at some data from Jordi Casam and Sergio Clara from the Spanish Pyrenees, here a coral, you can see that in the last 50 years or so there's been quite a striking increase in the abundance of diatom phytoplankton. And Jordi and Sergio, this is the location here, Jordi and Sergio were able to show from contemporary phytoplankton measurements that these diatom plankton essentially are growing in the autumn, and that there was a good correlation between the increased abundance of those plankton and the temperature through time. Good evidence that climate warming was in fact causing this apparent eutrophication of this remote lake. I've been Canada, John Small, and many co-workers, my own Douglas, looking at extremely remote sites and showing in many cases dramatic changes in the uppermost sediments. In this particular case, people published in Science as early as 1994, showing a massive increase in this diatom here, which is known to live on mosses. And the argument was that this lake had a permanent ice cover even in summer, but with global warming, that ice cover was reduced just to a moat, and the little zone was opened up to colonization by mosses and by different diatoms. And the point here is that this seems to be unprecedented over long periods of time, and therefore evidence not just of natural variability, but essentially of greenhouse gas forced climate change. And of course, we shouldn't forget that the climate system is extremely variable on lots of different timescales, and we can show this again from records from remote stations. And so in this case, in the Swiss Alps, work that Lotta published in 2002, evidence in the uppermost segments of an increase in the cyclotaric population, again suggesting warming. But if you go back through time, back to the Ice Age, you can see that the variation that's taking place at the present time is still within the natural range of variability of the climate system. It's difficult to argue necessarily from these data that we're dealing with anything other than natural variability, even though global warming might be playing a role, and probably is playing a role at this site. And then, of course, we can't always assume that these remote sites, in fact, really are only likely to respond to climate change, because we know from many studies, especially of toxic substances, but also from looking at nutrient data from around the Northern Hemisphere in particular, that our remote sites can be affected by long-distance transported pollutants. And Alex Wolf nicely showed from remote lakes in the Canadian Rockies evidence of diatom change or eutrophication, which could be related to warming, but in this case, he convincingly showed by measuring toxic lead concentrations and using stable isotope N15, that more likely that the change in these lakes in the Colorado Rockies was more likely due to non-range transport of nitrogen. And this is still a live issue amongst ethologists and paleontologists working in these remote regions to what extent can some of the changes which appear to be eutrophication-like effects in these remote regions be related to climate change, to long-distance transported nutrients, or perhaps to some combination of the two. So coming back finally then to the more populated parts of the world, we're still left with this question: to what extent can we identify climate change in systems that are either suffering from acidification or eutrophication and recovering from acidification or eutrophication. In our case, in terms of acidification research, we know there's massive reduction now in acid deposition that's taking place over the last couple of decades. And we have monitoring systems to assess the extent to which our streams and lakes in the UK are responding. What's unique about our monitoring record is that we have not only chemistry-biological monitoring taking place, but we've also got sediment transits like Diatoms entered on an annual basis. We can see from the monitoring data declines in sulfur, as we might expect, in the gradual increases in pH in the water column. And from the ability of living Diatoms, there are again some evidence that recovery is taking place. If we then plug these data from our sediments and Diatoms on the top of our sediment records, we can put these changes in a longer-term context. Here, going back to 1800, the pre-acidification community, the reference community, the acidification, and then the year-on-year changes in the Diatom assemblages. And in this case, evidence that slowly we're going back to the same Diatom compositions we had in the past. And the final slide shows that this is not always the case, because in this lake in Haggy, whilst the evidence of Diatom recovery is towards the dualistic composition, there are some species which are increasing, and therefore they are rather lower levels. Working with Gavin Simpson, we tried to put these data together in the context of our Diatom data from over 100 lakes in the PCA, and then we could use the reference condition back in 1800 to show that this site was in this place in 1800, acidification could be done to assemblages here. And the recovery process, instead of bringing it back down that line, is actually coming back, and it's coming back in kind of the septic trajectory. We don't know yet what the reason for that is it just random reasons, or in fact are we dealing with climate change and nitrogen deposition. We don't know, but this is just an illustration of the importance, I think, of connecting technology and technology and bringing the past and the present together and combining data sets in that way. And some conclusions there, but I think I'm going to stop and let you come. Okay, so the key conclusions. I think technology is now a powerful tool. It's making a unique contribution to limnology. It's an important tool in management of lake systems. There are many challenges for paleontologists per se, as the science of science are concerned with, for example, data improvements, new analytical techniques, understanding economic issues. But the key point I want to make is that paleontology of the future needs to continue to integrate with limnology to understand how and why lakes are changing through time, especially on these, if you like, intermediate timescales, the interhandle and decadal timescales, and then how we can use that combined understanding to protect and manage freshwater ecosystems in future. So thank you very much for listening, and again, thank you very much for the Patrick Award.